Hey guys, today we're going to implement Llama 3 model from scratch. I will try to explain everything in detail and step by step. We will be using mostly a PyTorch library and we will refer to the paper frequently, so I will put a link for it. And I will try to guide you visually through this diagram, and in the end, finally we will do a sample text generation with it. I've been trying to shoot this video for a while, but the last couple of months have been very crazy busy, so I actually shot the video in an extended period of time. And throughout the video you will see that my hair actually grows over time since I shot this video part by part over an extended period of time. I hope you enjoyed this video. I will put a GitHub link for the code we used in below, and as usual, if you like this video, hit that thumbs up, subscribe to my channel, comment it out, and share with your friends. Without further ado, let's start it. The first thing we want to do is go to the Meta website and download the Llama 3 weights. Since we load those weights into the Llama 3 model that we will code by ourselves. To do that, let's just go to the Meta's website. If you type Llama 3 Meta, it just opens this page anyways. So here you have to sign up and get an access to this model. They will send you an email and you will run a script that will download the model. We will do Llama 3 8 billion model, which will look something like this after you downloaded it. After that, just store the model somewhere that you can access. One last thing to do is let's look at the overall architecture of Llama. Let's go over this and see how it works briefly. If you understand this well, it will help you immensely in the upcoming sessions. At the bottom, as you can see, we have an input. We take that input and we feed it into an embedding layer. It goes through the embedding layer and it inputs to something we will call transformer block, which is the dotted line you can see here. First, inside this transformer block, it goes into this RMS normalization. And through this, it will go to the group query attention with KV cache section. Before this section, it will be calculated the values, keys, and queries. For queries and keys, rotary positional embeddings will be applied, which you can see here. That circle is for rotary positional embeddings. The output from this group query attention will be summed up with the input itself here. Then this summation will go to another RMS normalization. From this it will go a feed-forward SwiGLU section, and from here it will be added up with the output of the previous section here. And it will be out of this transformer block. After this, it will go through the RMS normalization again, a linear layer, and softmax. So a quick note here about is that during the implementation to the final Llama class, we won't include the softmax. We will stop here at the linear layer and we will take the output of the linear layer because the softmax will be used during the text generation part, which will be out of the scope of this video. We will only focus on implementing Llama 3 itself. However, we will do a sample text generation. Another note here is that if you look at this transformer block, the dotted lines here, you will see something called NX. This NX is the number of repetitions of this block. This is actually not just one layer, but this is multiplied by NX layers. So we will connect these layers on top of each other and stack them up according to the hyperparameter we give, which will be the number of layers. So if you want to stack 30 of them, there will be 30 of these transformer blocks that we will put on top of each other. And how we are going to implement is we will take everything element by element. We will implement the transformer block first as a class. Inside it we will have feedforward, SwiGLU function, RMS normalization, and group query attention with KV cache. After we have this block, we will actually build the Llama class. Inside this Llama class we will stack up this transformer block. We will have an embedding layer. After that, we already had the RMS normalization, and we will have an additional linear layer. And with this, our Llama 3 model implementation will be complete. You will be seeing this diagram. I think it makes things pretty easy to follow and also understand. Now, if you're ready, let's just get started. Since I'm on a Kaggle kernel, I will just do add input, and I have a model here called Llama 3. I will add this. Since to access this Llama model, you have to accept some conditions and stuff. That's why I didn't make my model public. But if you want to use the Kaggle kernel like I'm doing right now, what you can do is you can just create a new dataset and upload your Llama 3 8 billion model there and just add it as an input. And it will have these parameters. The next thing we want to do is, since I'm on a kernel, like Kaggle kernel, it can be a Colab notebook or whatever, we want to install some libraries. And those are tick token and blob file. This is for usually for tokenization. Okay, however, since like we discussed, I won't implement that. I won't implement everything, including the tokenizer. We will just go over to the transformer itself. But this tick token will be neat to see that our model is generating text and generate text by ourselves. So let's just install those. Now these libraries are loaded and it is time to import some other libraries. The first one is, as you can guess, we will import Torch. We will import NN from Torch. This will be mainly used to implement the neural networks. After this, we will import functional as F from Torch NN. We need our device. It will be CUDA if the Torch CUDA is available, or it will be a CPU. You will use this to put the tensors into the correct devices. Last, this may be an important part, we will set the default tensor type as bfloat16 tensor. So what it does is that it will basically make the Torch tensors half, okay? Otherwise, it becomes too big, and this is a big model anyways already. It may not fit into your memory if you don't do this, okay? Or depending on your GPU, you may need to use another Torch type, but probably if you do that, it will work and it will fit, okay? And let's just run this. Now let's continue with the hyperparameter definitions. We are going to start with the dimension. To get that, we will go to the Llama 3 paper, we'll go to the table 3 of the paper, and here we will look at the model dimension part. And here we can see that there are 3 variations of this Llama model: 8B, 70B, 400, and 5B. We will implement the 8B version. Okay, so we will look at this column. This column for the model dimension is 4096, so we will take that. If you want to implement 70B or 405B, and if you have the resources to load these models, you can just use these other values here. But we are going to go with the 8B version, so I will take this value, 4096. To continue, now what we have is the FFN dimension, which means feed-forward network dimension. This will be used in the feed-forward network part. So to get the values of this, again, let's go to the paper. Look at the table 3. Here we have FFN dimension directly, which says 14,336. We will get that, copy that value directly from paper again. And it is here. Now we have number of layers. Again, we go to the paper. We see there is a layers part. We are implementing 8B, so we look at under 8B. It is 32, so we take that value directly from the paper too. And put it here. Next one is number of heads. Again, we go to the paper, table 3. Here we have attention heads. We are using 8B, so it is 32. We copy that value directly from paper 2. As you can see, 32. Now we continue with number of k-value heads. So the thing here is we are using grouped query attention. So at the group query attention, what we do is we have different number of k-value heads and we group them under query values. I will put an image to here. So this means the number of k heads and the value heads will be different than the number of query heads, which we denote as number of heads, okay? So to get the number of k and value heads, again, we will go to the paper. Under the section 3.2 model architecture, we can see that they mention that they use grouped query attention, like we mentioned, with 8 key value heads. So they used 8 kV heads, okay? We take that value and put it through directly here. To continue, we have the vocab size. To get the exact number of vocab size, what I'm going to do is I will go to the parameters under the model file, which is params.json. You will have this file after you download the model. Here, we will see that there is a section called vocab size. This is basically the size of the vocabulary for the model we are going to load into our architecture. So I copy this value, paste it to here. This is our vocab size. We have normalization epsilon, which is, we will use it for RMSNorm. Again, we will take this from the model parameters.json file. When we go here, we can see that normalization epsilon is 1e minus 0.5. So I will take that value and put it directly to here. Now we have the RoPE data. For this, I will go to the paper and they mention something like this. It is just under the table tree. They say they increase the RoPE base frequency hyperparameter to 500,000. Okay, this is something new to the Llama tree. So we will copy this value and paste it here to the RoPE data. Another note about the vocabulary, they mentioned that they used 128k tokens, but to get the exact value, you have to go to the models and parameters.json file. Now we have the max batch size. So what is this? Is that it is the maximum batch size that your model can get. So it depends on your specification of the machine you are using. In this case, 4 was okay. Also, if you have one example or 2 examples for text generation, which we will see, it will take the lowest number. So if you have 2 examples for the generation, it will automatically set the max batch size to 1. But if you generate 5 examples simultaneously, it will take 4 of them for a single batch. So don't be surprised if you pass one example and see that your batch size is 1 when you output the layers. We continue max sequence length. This is the maximum sequence length that your model will generate. So this is also optional and depending on your machine. If your machine is powerful, don't hesitate to set it to a higher number. For this, I will just set it to 128. This indicates how many times we will repeat k and values to match the query heads. So again, I will put group query attention diagram here. What I want you to see is that when we are doing the multiplication, we will have a size mismatch if we leave everything like this, like in this image, because key and value are not the same as the query heads. They have different numbers. So in the code, what we will do is we will make them equal. But to make them equal, we have to know how many times we have to repeat k and value heads to be equal to the regular heads. That is very easy to find. What we do is we divide number of heads to the number of key value heads. So if we have 32 heads, in this case, we divide it by 8. So we have to repeat k and value heads 4 times to match the query heads, which we denoted as the number of heads, which makes sense because if we multiply 4 with 8, we get 32, which is the number of heads. So we eliminated the size mismatch. This approach has also some disadvantages that we will discuss during the implementation. Now we need the head dimension also. What it means is that it is the dimension per head. How do we define the dimension per head? Easy, we divide the dimension to the number of heads, which give us dimension per heads, which is called head dimension. Since hyperparameter definitions are complete and correct, we took them from both the model file and the paper, we can run the cell. Next is the RMS normalization and RoPE, rotary positional embeddings. However, I won't implement them. I will treat them as just helper functions because these are little functions and there are a lot of guides and tutorials on the internet that you can find. If we get into them, we deviate from the main architecture of Llama, okay, which is our focus. So for this, I will just put them here and treat them as a helper functions. Still, I put some statements to actually check how they work. If you want to go over them by yourself or by any other guide, you can just refer to these lines here. And let's just run this. Now it's time to do the first function implementation, which is the feed-forward network. If you look at this, you can see that it is just at the end of the transformer block with SwiGLU. That's the place we are implementing right now. And also why I started with this, because it was the easiest to implement. So let's get to it. We will define a class and I will call it feedforward, and we will inherit from nn.module. We will start with the init and we will put self. We will super from init. This is classical PyTorch. If you look at the diagram above, you will see that this is a SwiGLU feedforward network. The important part here is that it is a SwiGLU. SwiGLU has two components. First is Swish, which is a nonlinear activation function. And GLU gated linear units is basically element-wise multiplication of two linear layers, which one of them has to be activated by the sigmoid function. So if we combine Swish with gated linear unit, what we do is, instead of the sigmoid, we use the Swish activation function. So that's the thing. However, after we do that with two linear layers, what we will realize is that size mismatch problem, because with those linear layers, what we input is the dimension and what we output is the FFN dimension. And throughout the video you will see that we will try to match the sizes. To overcome this, we will add another linear layer and make it a feed-forward network. Overall, we will implement 3 linear layers. The first one is, which I will call W1, which is a linear layer which will take the dimension of the model which is dim and output FFN dimension with bias false. So as you can tell, since it takes the dimension as input, it will take one of the linear layers that will take the input of the forward function. This layer is one of the layers that we will use in the SwiGLU. As we discussed, we will use 2 of them in the SwiGLU and we will do an element-wise multiplication. Second one is, which I called W3, which is again a linear function which has to be with the same dimensions with the W1, because we will do an element-wise multiplication. And to do that, they have to be in the same size. Again, this is a dimension, which is the size of the input we will give it, and outputs an FFN dimension. So both to overcome this dimension mismatch, because in the end we will have a vector with FFN dimension, but we want a one with the dimension of dim, which is the model dimension, we will add another linear layer, which is W2, which will take this FFN dimension and output a dimension to us. And we will feed the output of the SwiGLU to the W2 and we will basically return that. To do that, let's define our forward function. If you're not familiar with PyTorch, what forward function does is that when you call the feedforward class, it will just go into the forward function with the input you provide, in this case x. And this is the whole formula. So let's get over to it. I will put again SwiGLU formula here. As we discussed, we have 2 linear layers, which is W3 and W1. We do element multiplication between them with a twist that one has an activation function. This is GLU in general, gated linear unit. When we put SwiGLU here, it becomes SwiGLU. Okay, so this case is the SwiGLU. This outputs dimension and FFN dimension. Now we need another layer which we defined here that will take this FFN dimension and returns us the dimension. And here comes the self W2, and we will just return that. Also, this SwiGLU activation function, we use it because the paper says that they use this activation function here at the table 3. All of them has the common SwiGLU activation function, which is implemented like this. It is always a good practice that after you implement a function, you have to give dummy inputs and see that if your function actually works. So we are going to do that now. I will have a dummy input which torch that generates random with batch size. 2 is batch size here. 8 is our sequence length. This is the sequence you give, like it can be, hi, my name is Uygar, this is the best YouTube channel. So whatever the length of that sequence, it will correspond to this. As a dummy, I gave batch size of 2 and sequence length of 8. And at the last, we give the model dimension dim. This will serve as our dummy input. Now I initialize our feed forward and I get the output by basically feeding this dummy input into this feed forward. So this dummy input will correspond to the X, this function will be called, this will be executed. So how it will be executed is that these two will be multiplied, with which gives us dimension to the FFN dimension, and then it will be fed into this W2. As we can see here, this all results will be fed into the W2, which will give us the batch size will stay same, sequence will stay the same, but as a result, we will get dimension at the end, so we expect to receive this dimension, which is batch size, sequence length, and dimension. So let's print the output and print its shape to verify that it is as we expect. And also let's delete feed forward here so that it won't take unnecessary memory in our machine. And let's just run the cell. And yes, it is just as we expected. Its shape is 2, 8, and the dimension which we defined as 4096, just like here. So we can say that this class feed forward with SwiGLU is working correctly. Now we are going to implement the attention, which is the core building block of any transformer model, in this case Llama 3 model. This attention is a group query attention with cache. Okay, so basically what we are going to do is we will do a group query attention. Basically, we will map some keys and values to multiple queries, and we will use something called KV cache, which will reduces our memory usage. These are all part of the Llama 3 implementation. We can also see that this is mentioned here. We used group query attention. We already put these values into hyperparameters and key value cache during the decoding. Okay, so let's get started. To make things simpler, I just called the name of this class attention. Okay, not a long name such as group query attention with cache, but that would be probably the most accurate name. As with any PyTorch function, we start with defining init and self, super.init. Now it's time to define the query key and value matrices. We define the query by a linear layer with input of dimension and output of the number of heads multiplied by head dimension. And bias is false. This is usually the case with the attention. We make the bias false. After this, we do something similar to key values, but the difference is, like we mentioned, this is a grouped query attention. So what we are going to do is, instead of multiplying with number of heads to the keys, we will multiply it by number of key v heads. Okay. We do the same with values. Instead of number of heads, we multiply it by number of key value heads. And last, we have an additional matrix, which is a weight matrix that defined in the multi-head attention formula. So what we do is basically, we will do a scale.product attention with queries, keys, and values, and we will output to this matrix. And for it to work, we need the output of these guys as input of this. So it is number of heads multiplied by head dimension, and we will output the dimension. So you might ask why we multiplied by number of heads, but not number of key heads. And the reason for that is, you will see in a couple of minutes, we will actually multiply keys and values to match the number of heads here. Yeah, it's a bit strange. I will also talk a little bit about it later when we get there. Continue, we will first start with the KV cache. What KV cache does is that, thing like this, every time we create new token, since this is a language model, we have to calculate keys and values of the previous sequence. So we don't want to do that because it is overhead and consumes a lot of memory. Instead, what we can do is we can store the previous calculation and we can reuse it. So I heard a good analogy for this, which is, think of it like you are reading something, and before reading a new word, you are rereading the whole section again. You don't want to do that, right? You read the new word and you go to the next word and you already remember what is behind. You don't reread the whole thing again. So this is something similar. First, to store them, we will create some empty matrices, which will consist of the batch size, your sequence length, number of key heads, and the head dimension. We put it to device since we will do operations on it. And then, since it is a key cache, as you can tell from the name, we will do the same for the values, max batch size, max sequence length, number of TV heads, and head dimension. And again, we put it into device. Now everything is set that we are going to use, which are matrices of query keys and values, and an additional weight matrix that it comes from the multi-head attention formula, and the empty matrices for keys and values that we will store the caches in. So we can move to the forward part. We will have several inputs. First is obviously X, which is the input matrix, input tensor. Start pose is where we are currently at the current token sequence, at our current input. For example, if your input has a sequence length of 8, let's say, it will start as 0 because we are at the beginning of the sequence. Then we will take every one of them and we will be at the 8th token, and it will be at 9th after that because we will generate one by one. And then it will be at 10, 11, etc. until your generation is complete. Frequency CIS is for positional retro embedding, and we obtain it from here, which is the output of this. Mask is basically the attention mask that we will use. By the way, let's just remove these two devices. I changed my mind because we will actually assign the devices to all these matrices during the forward pass. The first thing we do is we get the batch size and sequence length from our input. We can do it by just calling x.shape. The first parameter will be the batch size, the second will be the sequence length, third will be the dimension, but we don't need it, so we just put an underscore there. And let's put the shape of the x, which is input here too, which is batch size, sequence length, and dimension. And let's continue. The next thing we want to do is we want to actually input the X, which is our input, to our query, key, and value layers. So the key thing in implementing anything that machine learning or AI related is the keeping track of the dimensions. For example, in this case, we will have 3 outputs, right? Since we have 3 layers, one for query, one for key, and one for value. Now let's see what their output will look like. So the key and value will have the same output since they are the same, as you can see here. However, for query, it is different because it is number of heads instead of number of TV heads. So for query, we have batch size from input and sequence length from input. Alright, we put them there. And dimension in the last. So we input the dimension and we get the output of number of heads multiplied by head dimension. So we put that to here. And the same thing for keys and values, which is the batch size, sequence length coming from the input. Here inputs the dimension. Let's go for the key and value. And we output number of TV heads multiplied by head dimension. So we put that to here. Now, instead of for them to be multiplied, we want to add them separate as additional dimensions. Alright, so instead of number of heads multiplied by head dimension, we want to have a separate dimension for number of heads and a separate dimension for the head dimension. We have to do this because we will use it like this from the rotary embedding to the scaled dot product attention. So we did this for queries. We do this for keys instead of number of heads, number of TV heads as usual, and we do the same for values. So here I didn't write the dimensions because the sphere already tells us the dimensions. It would be unnecessary commenting. The dimensions are batch size, sequence length, number of heads, head dimension, or number of TV heads in this case. We apply the rotary embedding that we defined in the beginning. We applied the rotary positional embeddings only to queries and keys, as you can see in the image. The circles in the image represents the rotary positional embeddings, which are only applied to queries and keys, as you can see again in the image. And it returns us queries and keys. We input queries and keys and frex CIS, which is the output of the pre-computation. Now it's time for caching. The first thing we will do is set up the correct devices. So I would use mostly 2 devices instead of something like this, okay, whatever device we have. But now I'm switching to this 2, taking the input, which is queries, and just putting it to its device, because you may be doing a debugging on CPU, or you may be it's an Apple device. Whatever it is, if we take the input and put everything to input's device, we are safe and our program won't crash. So that's what I do now. we have the cache key for keys that we defined here. And I want to put it into the device of our input, which is queries. So I do the same for values too. The next thing is we will do actually the caching. So let's put the for values too. So this thing you see here may look a bit complicated or different, but this is NumPy array slicing. Basically, okay, you can just look it up. Basically, what we do here is that we take the cache key here. We take this cache key, which has the max batch size at the first dimension. Here, until the batch size, our current batch size, we slice it. Basically, we take those rows there. And then what we do is we go to the second position, which has the max sequence length, okay, which is here. We start at our starting position and we go until the starting position plus sequence length. So what we do basically here is that in the image you will see that there is a new addition to the keys matrix, to the cache keys matrix. That's what we are doing right now. We take the until the batch size over here, and then we take from the starting position, we add our sequence length, which is our all generated input, and we put the keys matrix here because we already calculated the keys here. So by doing this, we won't be calculating the keys again. And one more thing, the sequence length will be 1 after the first iteration because we will be generating only one token at a time, and we already cached the previous keys and values. So what we are going to do that the sequence length will be always 1 because we already have the previous computations. So we did this for keys and we add our caches for values too so that it is growing. Now what we want to do is we actually want to take the previous calculated keys and value caches that again you will see in the image. And how we do that is that something very similar. We go to the cache k and cache v. We take everything until our batch size. And we take everything until our starting position to the sequence length, which includes the cached values and also our latest keys and values because we already assigned them here. So caching out of the way, now let's continue with something about group query attention. So we will do something called keys.torch repeat interleave. As you can see in the group query attention, and we have been discussing, we have different number of heads between queries, keys, and values. What it means is that they have different dimensions. So we cannot work with them directly. What Llama does is that they basically duplicate keys and value heads to match the number of heads in the queries so that we won't get a dimension mismatch. We can see that in the Llama 2 paper. By the way, it is perfectly fine to look at Llama 2 paper when implementing Llama 3 since they implement the Llama 3 on top of Llama 2. So here, as you can see, they duplicate the KV heads for KV cache to be equal in the group query attention and behave similar. This is what this says. So how we can do that is we can just use something called torch repeat interleave. It will repeat as much as we want. For the keys, we put keys. For dimension, we put 2. And we already have the repeats we calculated in the Hyperparameter Definitions section. So number of KV head repetitions, we already have it. The input of this will be the keys, which is batch size, sequence length, number of KV heads, and head dimension. And output will be the same thing, but number of KV heads will be now number of heads. So we achieved what we wanted. We casted number of KV heads into number of heads, which will eliminate the size mismatch. This approach can seem a little bit different because why we casted number of KV heads and basically cloned it to match the number of heads. So why we deal with number of KV heads if we are going to match it to the number of heads anyways. That's how they did it, but I'm not sure this is the most optimal approach. Probably there are more approaches too, but this is the approach that Llama authors took. So we will just stick with it. We do the same thing for values. Instead of keys, we input values. Of course, number of KV heads mapped into the number of heads because we basically cloned them with repeat interleave so that it matches the number of heads. Now what we want to do is we want to do a little bit reshaping. Okay, we will do a scale.product attention and it expects a batch size and this 3 dots, that means that it doesn't really matter, or it can be not exist at all. and then it takes back sequence length and head dimension. But our currently input is batch size, sequence length, number of heads, and head dimension, which doesn't match this. So what we are going to do is we will just transpose it with 1 to 2. And what it will give us is that it will give us batch size, number of heads, sequence length, and head dimension, which matches this. As you can see, batch size is check, 3 dots with number of heads, check, sequence length, check, and head dimension, check. We do the same thing for keys, so that it matches the scale.product_attention input, and we do the same thing for values too. And as you can see, now keys, queries, and values have all the same shape since we did this repeat until leave. Now we will just do the scale.product_attention, which F module from PyTorch takes care. We just say F scale.product_attention. We will give queries, we will give keys, we will give values, and we will give attention mask that we took as input here. And the output of this will be the same: batch size, number of head, sequence length, and head dimension. After that is done, what this does is that we first take the transpose of the out, which will make things look like this: batch size, sequence length, number of head, and head dimension. And let's put a note here. This is sort of the transpose. It's like we undo this transpose we did. After transpose, it became batch size, sequence length, number of heads, and head dimension. We put contiguous, because otherwise PyTorch complains. And after that, we view it with batch size and sequence length and -1. What this -1 does is that it says PyTorch to take everything else and put them into one dimension. In the end, what we have after this view is that batch size, sequence length, and with -1, it just will multiply these, number of heads and head dimension, which will be equal to the dimension, and put it here. -1 does number of heads multiplied by head dimension equal to the dimension, which is the output format we want. Next, if you remember, we defined another weight matrix, which is VO, which accepts number of heads multiplied by head dimension, which is actually dimension, and outputs dimension. So what we're going to do is we take the out and put it inside that matrix, which again outputs the same dimension, which is batch size, sequence length, and dimension. And this comes from the definition of multi-head attention. With this, our attention is complete. Now what we want to do is, we always may do mistakes during the implementation. So we want to check that if everything works well with some dummy inputs. So we put a dummy input, which is a dummy batch size, which is 2, a dummy sequence length, which is 8, and a dimension. So I put 8 as sequence length, but it depends on your input. It will be always different. After you start to use KV cache, another node, again, it will be 1, but you can put anything you want. Dummy starting position 0, I put, and dummy frequency CIS. So as an input, I put 8 to 64 dimensions, and we need to put a dummy mask. In this case, mask size are sequence length to sequence length. Okay, so I put 8 to 8, and we call the attention here. We initialize it, and then we take the output and we put it the dummy input, which is X, dummy started position, which is starting position, dummy frequency CIS, which is the frequency CIS, and dummy mask as mask. We get the output and print the shape of the output. We expect it to be batch size, sequence length, and dimension. In this case, batch size is 2, sequence length is 8, and the dimension 4096, it is the same. We expect it to be the same as this. And then to free up some memory during the real application, we delete the attention. And let's just run this. We can see that output is 2,8,4096. Which is what we expected. We expected 2, 8 to the dimension, which equates to batch size, sequence length, and dimension. So everything is good, seems good with our attention, and we can move on to the next section. Now we are trying to connect some of the elements that we implemented together. Where we are going to implement is this dotted line box over here. This is the transformer block, and this is the actual layer that we are going to stack for Llama. So this layer will get stacked nx times, which is the number of layers times. In this case, we set it up as 32 during the beginning at Hyperparameter Definitions. And we defined the necessary elements. We defined feed-forward SwiGLU. We defined RMS normalizations. and we defined group query attention with TV cache. So we are ready to implement this block. And later on, when we put everything together, we will actually stack them 32 times from here. So let's get started. First, let's find our class. I call transformer block. So since this is PyTorch, we say nn.module. Continue with define init, self, super init. That was all the classical PyTorch things. Now we are going to define all these parts one by one. Self.attention, which is this guy over here. We define the feedforward as feedforward, which is this guy over here. We define the self-attention normalization. So we have two normalizations, right? One is this here, before attention, and one is before feedforward network. So we are going to define them differently. So first we define the self-attention normalization, which is this normalization. Now we are going to define FFN normalization, which is the other normalization that comes before the feedforward network, which is this. So we define all our elements inside init. Now what we want to do is we have to use them in the forward part. So let's define the forward. As input we have x, which is the input of our model. We have the starting position, we have the frequency CIS, and we have the attention mask. We discussed these parameters and what values they take, where do they come from, etc. in detail in the attention part. So I won't discuss them here. So our first line is this. Now I'm going to explain it to you one element at a time. First thing we do is we're going to start from the inside. We have the x, and we have the attention normalization that is applied to x. So x is our input. So x comes from here, and it is getting into the RMS normalization part, which is the attention normalization we define. And it goes out from here and gets into the attention, as we can see here. So this is actually what's going on here. We define attention with three parameters. One is the input. So in this case, this all green line we defined here that passes through the RMS normalization becomes the input of the attention. Actually, we defined it here. So we passed that, and the other parameters of attention were starting position, frequency CIS, and mask. So we pass those two. After we get the output of the attention, which is here, okay, output of this, if you look at the image again, is getting added again with the input here, because input comes from here. One, it comes from RMS normalization, and second, from the left, goes and gets added through the output of the attention to become here, become the output of that. So that's why we add one of x here, that is the leftmost arrow, and we define them as h. So here we have the h right here. To continue, we take that h, and as you can see here, again, h goes one directly to up and one to the left. The one that goes right directly to up is first goes through the RMS normalization. So we take the h and we put it into the RMS normalization, which we defined as FFN normalization in this case. And the output of this here goes through feedforward SwiGLU function. So we put that inside the self.feedforward function we defined, so that we are here right now. And there is another input that comes from the left, which comes from, again, the left here. So that is also h, as we can see here. And there's the addition parameter here. So what we are going to do is we are going to do h plus this, which is the output of middle arrow, so that it gives us the output. And we just return the output, and this will be the output of this transformer block over here. Now let's go through the dimensions a little bit. So the x, the input dimension, our x, is 2 to the 8 to the 4096, which is batch size, sequence length, and dimension. Again, in the transformer block, as we did with the previous functions, the dimensions don't change. Again, with batch size, sequence length, and dimension, batch size, sequence length, dimension, so we expect to output that. As usual, first, let's try and see that our function actually works. For that, we will use dummy inputs. Let's generate a dummy input, torch.random. We put 2 as the batch size, 8 as a dummy sequence length, and dimension. As a dummy starting position, I just gave 0, and we gave a dummy frequency CIS. In this case, I gave the dimensions as 8 to 64, We need a dummy mask with the dimensions of sequence length. Now let's define our transformer block. Transformer block equals to transformer block. Let's get the output. Let's give the inputs, dummy input as asks, dummy starting position as starting position, dummy frequency CIS as frequency CIS, dummy mask as mask. And let's print the output and output of the shape, and let's see that if it matches our expected shape. And our output is, as we expect, 2 to the 8 to the 4096, which is batch size, sequence length, and dimension. So transformer block seems to be working well. As you can see, when we do the small blocks first and connect everything together, everything becomes very easy to do. Now let me refresh the architecture page and let's get going. Now we have the K element ready, which is this block we just implemented, the dotted line block. Now it's time to connect everything and make the final Llama. Let's get started. We start by defining our class, which is Llama, and again classical PyTorch stuff, which is an module. Define in itself, super init. We do this at every time. Now we are starting to define the other elements. So as you can see, we have the transformer block ready. That is actually what we did until now. But now what we have to do is we have this embedding block that we don't have, RMS normalization, another one, a linear block, and finally the softmax. Now we are actually going to do them one by one. And we are going to start with the embedding one. With this nn.embedding, we put the inputs vocab size and dimensions that we defined in the hyperparameters, and that's it. We have the embedding done. Now we continue with stacking this transformer blocks nx times. This nx times in this case is number of layers. I don't know if you can read it, but it says number of layers. So to stack them, we have to store them at somewhere, and we are going to store them here. Torch.nn.module list. That's what it does. So we will iterate through the number of layers. At each iteration, we add a transformer block to the module list. This module list is like a list for PyTorch layers or PyTorch classes. In this case, our PyTorch classes are the transformer block, which is here. So we traverse this n times, n layers times, which is nx, and we add them into this self.layers. So in the end, we have nx times, or number of layers times, transformer blocks, which is the stacking part. Now we have the normalization part. We define that as the same as again, self.norm equals the RMS normalization, dimension and normalization epsilon, which we define again at the hyperparameters part. With this, we have this RMS normalization also done. Now we have the linear part. This part takes dimension and vocab size as arguments and outputs the raw digits. The arguments of this linear layer is dimension and vocabulary size, and it outputs the raw logits of the model. That is done. We don't apply the softmax here. That softmax will be actually applied during the text generation part. So we won't do it here, but still we can put a tick to see that we have everything we need. And the additional things we need to do the computations in the forward pass, we need the frequency CISs. We get it by pre-compute frequency CIS. We have been using it all the time, but now we are actually getting it. We give head dimension, max sequence length multiplied by 2 as input. And we give the RoPE data, and that's it. It will return us the computed frequency CIS values. Now let's move on with the forward part. I put torch.inference mode here, okay, because in that case it puts this to inference mode and doesn't do any training, but we will only do inference anyways, so you may remove this, okay, it is up to you, but I wanted to stick to the original implementation, so I put this. Now the forward function. We take the tokens, which will be our input, and the starting position, and which is the position that we are at. If we generated 3 tokens, then we are at this third position. If we generated 4 tokens, then we are at the fourth position, etc. Tokens, we get the shape of the tokens. The shape of the tokens for this will be the batch size and the sequence length. First, we start with the embeddings. So our inputs came, if you look at the diagram here, now we are passing it through the embedding with this. So we put the tokens inside the embedding and we put it as H. Now we take the frequency CISs. To overcome any device mismatch, we put the frequency CISs to the same device as the tokens. And we only take the frequency CISs starting from the start position to the start position added with the seconds length, because that's where we are right now. So here as default we say mask equals to none. Why we say that is that because when we start to apply the KV cache, the sequence length will be 1, and when the sequence length will be 1, actually we discussed it also before, we don't want to use any mask. So in that case, we want the mask to be none by default. However, if sequence length is greater than 1, in that case, it means that that is the first iteration. If it is the first iteration, it means that we don't have any KV cache yet, because we don't have any computations to store in. So in that case, we actually need a mask. So we are going to define it. We start by creating a tensor that has a size of sequence length to sequence length and filled with minus infinities. What this does is that attention doesn't attend to the minus infinities, so it becomes a big mask. When we do it by torch.full, basically it fills this whole tensor with minus infinities, so it becomes a big attention mask. However, we don't want to mask our own sequences, so we want attention to actually attend those sequences. So we don't want a big minus infinity tensor. So what we are going to do is we want to have a triangle like this. Okay, we want to take the lower triangle of that minus infinity tensor and make them 0, so that our sequence is not masked and the self-attention can actually be applied to our sequence. And how we are going to do it is we just say torch.triangle upper, we put the mask, this is our whole mask, we say diagonal equals to 1, and then this gives us that big tensor with the lower triangle including the diagonal filled with zeros, and the rest is infinity. And we put it into our device, whatever the token's in. It can be CPU or GPU or whatever. So this is important because we don't want to waste our resources on the tokens that we don't need, and we don't want to compute the attention values for them. So what we do is we just mask them out with this. Like I said, it is only done once when sequence length is greater than 1, because when sequence length is greater than 1, it means that we don't have a KV cache applied, so we are taking the full sequence, and while we are taking the full sequence, we want to apply a mask to it. Otherwise, mask will be none anyways, and the sequence length will be 1. After we have that, whether we have a mask or we don't have a mask, depending on where we are at our current sequence, we want to apply the transformer blocks. If you look at the graph at the right, we will be entering the transformer blocks we stacked here, and we want to get output from here. So how we are going to do that is, as you remember, we stored them in the self.layers. So we will iterate through self.layers, taking every layer in it, and we will give the age, which is output of the token embeddings. If you look at the graph, you can see here, output of the token embeddings, which we got here. We will give this to the transformer block. We will give our starting position, frequency, CIS, and masks. It will return us the age, and with the new age, we repeat the process until we traverse all the transformer block layers. And in the end, we will be traversed all the stacked transformer blocks, and we will be out of this big red area. As a result, we will again a variable h here as output of this transformer block. So if we look at the graph again, what we do is after we are out from this transformer block, we go through the RMS normalization, right, with our variable h. So that's what we are going to do. We take the self.norm we defined and we put the h in it, and again we output the h. By the way, let's also keep track of the dimensions. As we previously did, the output of the transformer block is batch size, sequence length, and dimension. In this case, the dummy inputs that I will give, it will be 2, 8 to the 4096. And the normalization output will be the same also. And now what comes after the RMS normalization? If you look at the graph, we can see that there's a linear layer. So that's what we want to do now. We take the h and we defined our linear layer as self.output, and we input the h into that self.output, which is the linear layer. So in the case of linear layer, we defined as dimension to the vocab size. Okay, so instead of this dimension, the output of this linear layer will have the dimensions of batch size, sequence length to the vocabulary size, because that's how we defined it here. The output's the vocabulary size. For softmax, as we discussed, it will be used during the text generation part. And as a result of this, we are only interested in the raw logits from this linear layer. So we will just return the linear layer with the sizes, batch size, sequence length, and vocabulary size. As usual, let's just try it with dummy inputs and see that if our function, this whole transformer architecture or Llama architecture, works or not. So again, we will create dummy tokens. Up to now, I was using random n to create these dummy tokens. However, random n generates also negative numbers, but the function we used for embeddings, nn.embedding, only accepts positive numbers. So if you use random n, you will get an error with the embedding. So we have to change it to only random. As dummy size, our classical dummy size with batch size 2 to the sequence length of 8. And also if we give the sequence length of 8, we will be also testing if our mask works correctly or not. And we put it into the long, because that's how it accepts it. We give a dummy starting position, which is the 0. Also, if you have the sequence length of 8, it means that, again, since we are using KV cache, it means that it is your first initiation of the function. Then you have to be at the start of your sequence, then your starting position has to be 0. Now we define the transformer equals the transformer, we initiate it, we feed our dummy tokens and dummy starting position to our transformer, we get our output, and we print our output shape. So what we expect is what we returned. 2 to the 8 to the 128,000, which is here. That's what we expect, which is batch size, sequence length, and vocab size. And in the end, to free up some memory, we delete the transformer. And let's run this and let's confirm that we get the correct results. Now, after I run the model, I get this size, which is batch size, sequence length, and vocabulary dimension, which matches what we output and what we expect. So we can recon that this function is working correctly. With this, you have implemented the Llama tree. So first of all, congratulations. And if you want to use your Llama model, you have to just call this transformer class. You can train it if you like and play with it. I will do a sample text generation with this model that we implemented to demonstrate that it actually works and have some fun with it. However, implementing the text generation part is out of scope of this video. This video is for implementing Llama tree, which we did. So I won't be explaining what's going on. The code for the text generation, I took it from Meta's GitHub repository, which I will link below, and made some small changes for it to be applied to our parameters and our custom model. Let's see how it goes. This chunk, this cell, is used to generate text, tokenization, etc., that kind of things. If you like, you can go over it by your own. One of the small changes that I made, or debuggings I made, is in this line, we will print how many parameters does our Llama model have. So what we expect is to our model to have 8 billion parameters, because that's the parameters we took from the paper, and that's the model we loaded, that's the model we built. So we will confirm that our model actually has 8 billion parameters on the go. Now the necessary functions to generate text are defined in the upper cell. Let's actually test the text generation with the Llama tree model that we built. Here, to checkpoint directory, we will put where our model is located. In my case, it is under Kaggle input Llama tree, and the tokenizer path, you will put your tokenizer. When you download the Llama tree model, which I showed in the beginning, you will get all of these anyways in that downloaded file. And the tokenizer path, in my case, it is the tokenizer.model under Llama tree. Here are some parameters: temperature, top P. I explained them in my other text generation videos. If you are curious about them, just check them out. In this case, I will leave them like this. Max sequence length, I put 128, max gen length 64, and max batch size is 4. So you can play with them to generate different texts with different lengths. It's up to your specifications. After that is done, we will create a generator object from llama.build, which is from the big chunk of code that we pasted at the previous cell. We pass the parameters we defined previously, and then we define a couple of prompts by ourselves. These were the default prompts from the Meta's GitHub. I believe the meaning of life is, simply put, the theory of relativity states that, and we expect our Llama 3 model to complete these. And also you can see that since we have 2 prompts in total, it means that our batch size will be 2 for this run, even though max batch size is 4, because our total number of prompts are smaller than the max batch size. To get the results, we simply call generator.textCompletion. We pass the prompts we defined and other parameters such as max gen length, temperature, and top P. After that is done, we will just print the prompts and the results like this. Now let's run the cell and see the number of parameters in our model as well as the generated texts. And now we have our outputs. First, we can see that our number of parameters, this is 8 billion. So we can get a satisfaction to know that we successfully implemented the 8 billion Llama 3 model. Loading time, and most importantly, the prompts and their generations. So this is the prompt we gave, and this is the text generation we got. Depending if you change the parameters of text generation, this may be a little bit different. This may be longer, shorter, but you will get a meaningful text like this that is generated by your own implemented Llama 3 model. Also note that we did all these on a 16 GB GPU thanks to our PyTorch settings. This GPU is very easily accessible to everyone for free. So that was all for today. Thank you for watching. We implemented the Llama 3 successfully, which was the scope of this video. And additionally, we generated some text to show that it is working and to have some fun. I hope you now have a better understanding of the Llama 3 architecture, how it works, which element does what, etc. Don't hesitate to play with this code, change it, generate different texts. And as usual, if you like this video, leave a like, a comment, subscribe to my channel, and see you at another video. Thank you for watching.